This is your lesson for 3-6 theorems about roots of polynomial equations. And our central question for this, how are the roots of a polynomial equation related to the coefficients and the degree of the polynomial? So we're going to dive deeper into looking at some helpful tips to decide what our roots of polynomial equations are going to be. So our first concept here is the rational root theorem. So let's say we have a polynomial here. That's what's listed there with the polynomials in decreasing order, or with the terms in decreasing order, be a polynomial with integer coefficients. If the polynomial equation p of x equals 0 has any rational roots, so if there are any rational roots that exist, then each rational root is of the form p over q, where p is a factor of the constant term a sub 0, and q is a factor of the leading coefficient term a sub n. So you're always going to have the form p over q. Your p is going to come from the factors of your constant term. So in this example that I've written out here, your constant term is -3. Well, all the factors of -3 are going to be plus minus 1 plus minus 3, because we could have 1 times -3 or -1 times +3. The q term is going to come from the factors of the leading coefficient. Well, my leading coefficient is 7. The factors of 7 are plus minus 1 and plus minus 7. Positive 1, positive 7, -1, -7. And then you go through and find all of the combinations of the possible p's over the possible q's. You can list the plus or minus, so really you want to think about the fact that there's double the amount of possibilities than what you see, because you have the positive and negative of each version. So if I start with p is 1, I could have 1 over 1, which will simplify to 1, and I could have 1 over 7. Then if I move on to the p of plus or minus 3, I could have 3 over 1, or I could have 3 over 7. So altogether, this is going to simplify to plus or minus 1, plus minus 1 7, plus or minus 3, plus or minus 3 sevenths. So if this polynomial were to have any rational roots, it would have to come from this set of 8 possible answers. There is no possible way that this could have a rational root that is anything other than what is listed here. So this really does help us narrow down, especially if you need to pick and choose what your roots are going to be. This gives us a much more narrow pool to pick from. Notice I wouldn't bother testing 2, I wouldn't bother testing 4, anything like that, because they are not part of the p over q set. So that brings us to our first example. It says from the graph, it appears that 4 is a 0 of the function. Without substituting, how can you determine if 4 is a possible solution? So we aren't going to do synthetic division. You could do synthetic division and test very quickly, but it says how could you do this without plugging it in, without doing that synthetic? So we're going to look at our possible p's and our possible q's and our possible p over q's. So my p is -4. Those factors are plus and minus 1, 2, and 4. Q is 8. So those possible factors are plus and minus 1, 2, 4, and 8. And now I would do all my possible p over q's. So if I start with the p is 1, that's going to be 1 over 2. I'm sorry, I skipped the very first one. 1 over 1, plus minus 1 over 2, plus minus 1 over 4, plus minus 1 over 8. Then I move on to the 2. So I have 2 over 1, 2 over 2, which is actually a repeat, so that would be the same as 1 over 1. 2 over 4, which is also a repeat of 1/2, and then 2 over 8. And then I have 4 over 1, 4 over 2, 4 over 4, which is a repeat, and 4 over 8, which is a repeat. So if I go through and simplify these, my possible P over Qs are 1, 1/2, 1/4, 1/8. 2 over 1 is 2. 2 over 2 is a repeat, because that's the same as 1. 2 over 4 is a half, that's a repeat. 2 over 8 is a fourth, that's a repeat. Then I have 4. 4 over 2 is 2, which is a repeat. 4 over 4 is 1, which is a repeat. And then 4 over 4 is a half, which is a repeat. So if we look at our possible solutions down here at the bottom, you can see that 4 is a possible P over Q value. So because 4 is a possible P over Q, then 4 would be a possible answer for this solution. Okay, now we're going to dive into a problem where we're actually going to go through and solve. It says a storage company is designing a new storage unit based on the dimensions shown. The volume of a container is modeled by the polynomial v of x is equal to 2x cubed minus 7x squared plus 6x, where x is the width in feet. What are the dimensions of the container if the volume of the unit is 154 feet cubed? Now you can see here, they give you the x, the 2x minus 3 and the x minus 2. This is, I know it kind of looks like it's slanted on the top, but we're considering this to be a type of rectangular prism. They've already gone through and multiplied those 3 dimensions together. That's how you get the 2x cubed minus 7x squared plus 6x. And we know the volume is 154. So we are going to take that volume and set it equal to 154. Oh, not B. So the polynomial that I'm really solving is this. Now, there are a lot of different factors for here, and I need to go through, rather than just randomly picking values to plug in using synthetic division to figure out what my x can be. I need to go through and figure out what my possibilities are. So my constant term, my p, is negative 154. And I'm actually going to write that down below because that gives me a little bit more space. I'm going to use different colors here too. So my p is negative 154. All the factors of 154. And I'm only going to write the plus or minus once out in front and then write everything else. So all of these are assumed to have plus or minus. 1, 2, 7, 11, 14, 22, 77, and 154. And yes, you would have to go through and just divide to make sure that you didn't miss any of those factors. My Q term is 2. That's a little bit easier. My factors are going to be 1 and 2, both with plus minuses. So now I have to go through and list all the repeated values for P over Q. And I am going to go through and simplify these. So starting with the 1, I have plus minus 1 and 1/2. And then I'm going to have 2. 2 over 2 is a repeat, that's the same as 1. And then I go to the 7. So I have 7 over 1 is 7, and then 7 halves, 7 over 2. And then I have 11, which is a new one. 11 over 2 is new. 14 over 1 is new. 14 over 2 is the same as 7, so 14 over 2 is a repeat. Then I'm going to have 22 over 1. which is 22. 22 over 2 is 11, which is a repeat. 77 over 1, which is new. 77 over 2, which is also new. 154 over 1, which is going to be 154. And then 154 over 2 is a repeat. It's the same as 77. So that is going to be, those are all my possibilities. So now I'm going to do some synthetic division until I find something that works. Now you can be reasonable about this. For example, any of these values that would give you negative dimensions are not going to work. And keep in mind that if we multiply x times x minus 2 times 2x minus 3, I need to get 154. Well, 154 itself, if x was 154, you'd have 154 times 152 times whatever 2 times 154 minus 3 is. That's going to be way, way, way too big. So that is not going to be a reasonable answer. 77 likewise is going to be too big, as is 77 over 2. 22 you can probably rule out as well, because 22 times 20 is going to be bigger than 154, so we can get rid of that one as well. 1 is not going to work, because if I were to plug in 1, 1 minus 2 gives me a negative dimension, so that one doesn't work. The same with a half. 2 would give me 0 as a dimension, so that does not work either. 7 is reasonable, 7 halves is reasonable, 11, 11 halves, 14. Those are all better numbers to be working with. Another thing to note about this, because we are talking about the real world, we are only going to be using the positive values. We can't have negative dimensions for a shed. If this did not give us any context, then you could go through and test for the negatives. But because we are, again, looking for a dimension, or 3 dimensions actually, I only want to use the positive values. So I'm going to set up and test a couple of these. So let's try 7. So my polynomial, I have a 2, a negative 7, a 6, and a negative 154. So again, I'm going through and doing my synthetic division. 54 there. 54 times 7, 8 carry the 2. That's 378. So that's a no. 7 does not work. I tested it, did not work. That does give me a positive number, so it looks like I actually need something that's smaller than 7. So let's try the 7 halves. So 2 times 7 halves is 7, gives me a 0, 0, 6. 42 over 2 is 21. So that is actually too small because I'm on the negative side. So if 7 was too big, 11 and 14 are going to be big. So the next one that I want to try is that 11 halves. So bring down the 2 times 11 halves is 11. Add, I get 4. 4 times 11 halves is going to be 22, which gives me 28. And then 11 halves times 28, well, the 28 and 2 reduce to become 14 and 1. 11 times 14 is 154, and that does give me the 0. Now, there is only one real solution to this. 11 halves is going to be my solution. So the dimension of x is going to equal 11 halves. The x minus 2, if I take 2 away from that, that's going to be 7 halves, or 3.5. And then the 2x minus 3 is going to be 2 times 11 halves, which is 11 minus 3 is going to be 8. So this is, if you want to change to decimal, 5.5 feet by 3.5 feet by 8 feet shed. Okay, so that's one of the ways you can use this theorem to help you solve a real world type question. This brings us to the fundamental theorem of algebra. So if p of x is some polynomial that has a degree that is greater than or equal to 1, and p of x equals 0 has exactly n, or then p of x equals 0 has exactly n solutions in the set of complex numbers. So what this means is if you have a polynomial that is degree 3, it has 3 solutions in the set of complex numbers. Now, those solutions could be a mixture of complex and real. They could all be real. They could only all be complex if you have an even number, and you'll see that actually a little bit towards the end of this lesson. But also you need to consider if any of your factors have a multiplicity, that counts for that amount of times. For example, the equation x minus 3 to the 4th, that has 4 solutions, but all 4 of those solutions are 3. Because the solution of 3 has multiplicity 4, so it counts 4 times. So you do need to be aware of what the multiplicity is whenever you're actually looking at these types of questions. We're going to wrap this video up. I'm going to make another video with the second part here. But I think that's enough for this first one, just to kind of give you guys a little bit of a split here. So when we come back, we will get into using this fundamental theorem along with the rational root theorem to solve another polynomial that's not a word problem, it's just in a general context. And then we're going to go back and talk about those complex numbers having to be of even degrees or even amounts. So go back through, rewatch this video, reach out to me if you have any questions.